Let's start by writing out the combined reactions here. So we recognize that there's 2NO that's going to be reacting with an oxygen group to produce 2NO2 gas after we've taken out all of the intermediates, which in this case is just the N2O2. So let's take a look through now and take a look at the experimental rate law, which we see is given to us as being kNO squared times O2. And that makes total sense just on quick glance if we're talking about the rate of change of nitrogen gas, but we can go ahead and figure this out for ourselves. So the rate at which nitrogen is going to be consumed in this here, assuming that these steps are assuming that we have the rate at which it's being produced minus the rate at which it's being consumed. So we'll have delta NO produced over delta T minus delta NO consumed. So for this, we go ahead and we ask, okay, what is producing it? Well, we have our rate law K minus 1 times the amount of N2O2 and then the amount of stuff that we have consuming our NO is just our K1 times NO squared. Okay, but now we need to figure out what the amount of N2O2 is. So the amount of N2O2 we're working with is changing over time. And actually, because we realize that it's an intermediate, we recognize because it's going to be an intermediate, we can assume by steady state approximation that the change over time is roughly 0, which means that the amount it's being produced is equal to the amount it's being consumed. Now, where is it being consumed? Well, it's going to be consumed in the second reaction. So that means that K2 times N2O2 times O2 is going to be equivalent to the rate at which it's being, hold on. There's one other guy here. So we have the amount at which it's being consumed, but it's also going to be consumed by the reaction going the opposite direction. So we have our amount of N2O2 times K minus 1, which is going to be approximately equivalent to our K1 times NO squared. Okay, that's a fair bit that we've got to take in right here, but that's okay. Let's go ahead and work through it. So let's go ahead and separate out our N2O2, which is going to equal K1 NO squared all over, we now have O2 times K2 plus K minus 1. Okay, now let's go ahead and substitute that back in to our first expression. So we have K minus 1 times K positive 1 times NO squared over O2 times K2 plus K minus 1. And then we have all of that, which is going to be minus K1 NO squared. And because we want it all to be under a common denominator, I'm going to go ahead and expand this out. That's going to be minus K1 NO squared times K minus 1, and then again minus K1 NO squared K2 O2. Goodness, that's a lot to take in. But that's okay because this is about to simplify down a lot. We go ahead and we substitute all of this out right here because those two terms cancel, and we end up with negative K1, K2, NO2, NO squared rather, times O2 over K minus 1 plus K2 O2. So thus, we see that it is related to the original rate law, which we completely expected, which is K1, K2, and we can approximate that this value is going to be very, very small. So we can approximate that down to 0, and from there we get our K1, K2 over K minus 1 times NO squared O2. Of course, that is entirely negative. Now, if we really wanted to, we could crunch all of this down and we could realize that in fact this goes to approximately, if we don't make this assumption, we'll find that this goes approximately to 2K1, K2 over K minus 1, K minus 1 times NO squared times O2. And once we go ahead and do this, we realize that this guy right here, this term right here, is big K.